the first speaker will be Martin Gannholm. He ran the teams that built several key cloud products at Google, and he'll be talking more about that. So please join me in welcoming Martin to the stage.
Thank you. All right. Well, I'm excited to be here. When I first was asked to do a presentation here, I assumed I would get at least an hour to talk. And then, I found out just a few days ago there was only 30 minutes, and I had to redo everything. But hopefully I'll share some interesting anecdotes and some of the thinking that went into, and some of the work that went into building some of the cloud products at Google. And so, this is just a quick word cloud on products I worked on over my career, and companies I worked at, starting sort of at Apple and, doing a bunch of interesting stuff. So Compute Engine and Kubernetes are sort of the two key things I'm going to talk about that I worked on at Google. And so let's jump in. So building Google's cloud, I didn't really know anything about infrastructure when I came to Google. My career sort of has three segments, each about 12 or 13 years long, and sort of my infrastructure and distributed computing started when I started at Google in 2011. And when I got there, Google already had what I call a proto cloud. They'd built all this amazing stuff, all this amazing technology, which Google uses to build all of their stuff. Everything's built using these things. And the top thing there is container orchestration. You probably have heard of Borg. And if you haven't, it's sort of the big brother to Kubernetes. But they had all these other building blocks that you could use when you built things at Google. Now, it wasn't easy because it's kind of very complex and sort of made for serious stuff. But we had those shoulders of giants to be able to stand on to build Google Cloud. So one example, so I came in just as Google Cloud Storage was getting finished to sort of manage that team, and they had to build a high availability control plane. They had to sort of do customer counts and billing, because that was sort of the first thing we needed to do in cloud. Blob Store was something that Google had already built and used internally for all of its internal things, all the things that you would use at Google, and an admin console, a command line tool. So the list of things to build wasn't that big, right? So there were 5 people, there were 5 engineers that built cloud storage. When I took over the team, a few months later, they asked me to take over this other team, which ended up being Compute Engine. So this is the virtual machine infrastructure at Google, which interestingly, when I took it over, the reaction I got from other Googlers was, why would you do virtual machines? That's just stupid. There's a much better way to run things. We should run containers. And of course, the answer is that virtual machines is what people wanted, right? That's what they knew, that's what they understood. And we actually had this conversation with my leads that we really wanted to offer a cloud version of Borg, which is the container orchestration system, but it was just too hard. We knew that would not hit the market properly, and also the whole idea of containers, sort of the benefits of containers, the encapsulation and the portability and all those things, was something that was going to be hard to explain. But anyway, so we built Compute Engine. The first 4 things were sort of the same as we needed to do for cloud storage. And then we had to do some actual real work to actually implement all the virtual machine stuff, because a lot of that stuff was not compatible with the internal Google systems. They didn't have virtual disks that you attached to VMs. We had to build that. We had to do encapsulated networking. We had to do a lot of different things that try to work inside of Google's infrastructure. Now, one interesting thing that I'll mention is that when you run a virtual machine at Google, that virtual machine is running in a container in Borg. Just let that sink in a little bit. And so that's kind of interesting, because when you have a container orchestration system, it's kind of a lot easier then to do provisioning of your virtual machines. All you do is you say, I want a container, and it goes and finds a machine to run it on. it sort of maintains that and all that kind of stuff. Of course, one of our biggest problems was the suppression of preemption. So preemption is where, the Google container system would say, you know what, we need to kill a task. Everything is stateless, we just need to kill something, and we need to move it to a different machine. And you, of course, don't want that with a virtual machine, because a virtual machine is actually stateful. So we had to do a lot of things. Live migration was another very tricky feature that we had to build, where while you're running your machine, if the infrastructure decides that it can't keep running it on that host, it will start copying all of the memory over to another machine over the network, and then you'll take some few milliseconds outage while it actually moves the very last piece, and then your code will continue executing, your VM will continue executing on a different host, right? And that could be across the data center, it could be on a data center next to it. And so this happens all the time when you run virtual machines in Google's cloud, that you're running your VM and you don't even know that it's actually being migrated. So, so that was quite an effort. I started with 18 people, and I guess there were a few hundred people that eventually ended up shipping Compute Engine. But that was a fun project. And so some of the stuff that's underlying how Google builds stuff, and I think a lot of these principles are now sort of well known in the industry. But when I started at Google, my mind was blown. When I got to Google, I had 25 years of career behind me, and I thought I'd done everything, right? I'd done consumer software and hardware at Apple. I'd done enterprise software. I'd done games. I'd done a variety of things. And I got to Google in my very first week. My reaction was, honestly, I don't know anything, right? And so I had to learn all about distributed computing, all about this idea that these principles, for example, like expect failures, right? Machines are going to fail. Networks are going to partition, right? Unplanned things are going to happen. So you just need to plan for unplanned things happening, and that just means that you got to be able to detect it. You got to fail gracefully. You need to build resilience into your systems. You need to have playbooks. You need to anticipate and say, well, what are we going to do when X happens, right? Or what are the steps we're going to take to figure out what's wrong when something bad happens, right? And then MTTR, mean time to recovery, is sort of the key metric, right, that we would use to say things are going to fail, and that's fine, and we'll fix them. And what we try to do is to fix them as quickly as possible, get things back to a stable state. And one of the techniques we had to sort of test this is to run these DIRT exercises, or disaster recovery testing. Chaos Monkey is like one example of what happens if you just start randomly killing stuff in your production environment. How does the rest of the system react? Does your detection systems, your monitoring, do they detect those things? Do you have automated recovery procedures that are kicking in? So, doing those simulations is key, right? But expect failures, I would say, is probably the number one principle. Cattle, not pets, right? You don't want to have pets in your environment. I'm sure you've heard that saying. And so stateless is good, right? Obviously, you can't always be stateless, but having that principle of thinking about as much stuff as possible that can be stateless, you can temporarily read some state from some storage as you get a request, and then once your request is done, you drop the state, right? So you're not carrying it around, and that way you can get scale, and you can do deployments, and sort of all those kinds of things are much easier to do because no individual replica of a job, of a piece of code is special, right? They're all the same. The second point there, no special recovery flow, right? If you're you don't have to refill caches or do anything of those things if something fails, because your expected thing is that as soon as you get a request, you get all the information either as part of the request itself, or you go and get some additional stuff, and so there's no setup in order to actually recover from failure. And there's also you reduce the codependency between different component instances. So if you have one service that's calling another service, in some systems it's very common to say, well, this service handles, A through C, and so this backend service also, handles A through C, so they kind of need to be linked. These guys only talk to those guys, and there's a different set that handles some other sharded range of inputs, right? And so if everything is stateless, then any front end can call any back end, right? Okay. Separation of concerns, another sort of key principle. And so the factoring of system into components has a bunch of benefits, but so they need to be loosely coupled, and they need to have narrow contracts. And I think the contract is sort of the most important aspect, is that you figure out how, what is the agreement between this component that calls this other component, right? And so that's what you start with. And the benefits are that you can independently deploy these things, right? You can upgrade this one without upgrading the second one. They're independently scalable, so if you find that, the amount of work that the back-end half of this process is doing is actually much more heavyweight and takes longer, and then you sort of have the front-end pieces that are sitting idle, or you're getting a backed-up queue because they're not in balance, right? And it's hard to predict exactly how many you need of each one, but if each one can scale independently, then you sort of just let automation deal with that. And then swappable implementations is sort of a key function too, where if you are developing something and you need to have a database, for example, if you have a contract to talk to a database, you don't care if it's talking to SQLite on your local machine, or if it's talking to Cloud SQL at Google, or if it's talking to some hosted SQL instance in your data center, right? Because you've decided what the contract is. So that general principle is important. I'm not going to talk too much about security because I'm not a security expert, and I know that a lot of people here know a lot more about this than I do. But just some of the different layers of security, defense in depth, obviously, and having all the different security layers and ability to sort of protect your data, your processes, and your production environment. Okay. So. I don't really like the word testing. I like talking about how do I get confidence that what we built is right, that it's going to function correctly, right? So I always talk about building things with confidence. Obviously, you're going to have testable code. You're going to run things. You're going to have simulations, or you're going to have both integration tests and those kinds of things. And really important to automate everything, right? So as much as you can, you automate. And so this was something that Google does really, really well. They just want to automate everything. And so you build these systems, you build these infrastructure pieces, you build pipelines, everything has a high degree of automation. And then you do monitored rollouts, so you can do blue-green deployments and automatically have the feedback loops from your monitoring to sort of detect whether the rollout is successful and then automatically back out if it doesn't. So those are some other principles. I think that's my last one of those. Okay, so what do we do after this? So after this, a couple of the guys who worked with me on Compute Engine, they sort of came to me and said, hey, there's this fun new thing, like some guy did this thing called Docker. It's pretty cool. It kind of has some of the same ideas, using the same Linux features that sort of Google pioneered that they were using in Borg, with C groups and those kinds of things. And this guy put together this package called Docker. And it's really actually very cool, and it looks like people in the outside world are starting to play with it, and they're starting to appreciate some of the interesting characteristics that it gives you, right? Whether it's sort of the packaging of it, the layering, and the portability and all those kinds of things. I can run the same code on my laptop and the same code in a data center on a large host, and the behavior is going to be the same, right? You can sort of trust that it's really going to work. And so they went off and played with this for a little while, and they said, "Hey, Mr. G, come play with us. We're doing this thing." And I'm like, "Well, I'm running this compute engine team. Why don't you guys figure out if there's something there? And if there is, I'll come help you build a team." So they came back a few months later and they said, "Okay, we figured it out. We're going to build this thing." And then, at that time, it was called Project 7, but it ended up being called Kubernetes. And so I ended up building the Kubernetes team, and we sort of did the open source Kubernetes. And the thing that we did, so Docker opened the door to that, right? The interesting thing about choosing to do open source, because Google had done a few other interesting inventions over the years, right? And so MapReduce was probably one of the early ones that ended up having an open source equivalent, or sort of an attempt to do the kinds of things that Google's white paper talked about, right? So Hadoop got this big ecosystem built around it, where people were building tools, they were building all sorts of higher level constructs on top of Hadoop, right? And it's still a very big ecosystem, right? And so we said the success of Google is not just because Google had Borg, but it's because Google actually invested an enormous amount of effort into building all the tools and all the the pipelines and the monitoring and the deployment pieces. All of those things were built internally at Google, and at Google scale, they had tens of thousands of developers, so it was a reasonable investment to make. But it would be hard to replicate all of that on a new sort of container orchestration system in Kubernetes, right? So you said we need help, right? So if we open source it, then people will say, "Oh, this is cool. We'll build something on top of this," right? And you can see that Kubernetes has a very rich ecosystem of tooling and capabilities on top, right? I usually talk about Kubernetes being it's like assembly language for building infrastructure. Is kind of how I think about it. Because people usually say Kubernetes, "Oh my God, my head hurts." They're like all these little pieces, I have to piece them together in exactly the right way, and so you have these atomic little building blocks, right? And that's true, and you can build almost anything with Kubernetes, I believe, right? But it's kind of like doing it in assembly language. And so I think the goal is that more and more higher level constructs get built on top of Kubernetes, so that you can actually use the metaphors and the constructs that make sense. You can build some yourself, or you can get them from the open source community that are building these things, right? They build various systems on top of it. So that was a key thing, is to sort of have a system that allows for that interplay between, you can augment the system yourself, or you can get augmentations from third parties. Key thing, of course, also with Kubernetes is that it's agnostic, right? You can run a Kubernetes cluster on your own machine. You can run it in any one of the clouds. You can run it in your on-prem, and have a reasonable certainty that things are going to work, right? If you run it here, it's also going to run over there, right? So there were a few things that we did with Kubernetes that were not present in Google's Borg, right? So we sort of simplified. Well, it's much simpler than Borg. If your head hurts from looking at Kubernetes, believe me, Borg would hurt your head 10 times more. But there were a few things that we'd learned from Google's internal systems, and we made a better system, right? And so sort of the reconciling controller pattern that exists in Kubernetes was something that did not exist in Borg. And so that simplified a lot of things. It allowed you to create additional functionality that was layered, and you could add capabilities without recompiling or touching the code that was doing other things, right? And so the extension mechanisms, among them custom resource definitions and aggregated APIs were another thing that we're like, you need to be able to add to this thing without having to then go in and recompile the base system. So I sort of said this on this slide. I sort of think of Kubernetes as the infrastructure operating system for the rest of us, right? So it's the thing that sort of you run everything on top of. It's not the thing that answers every question, but it's a good starting point, right? It's a sort of a portable starting point for building systems and software on, right? So building high scale, building reliable systems, it's a good starting point. Pods was another innovation we came up with. Borg had this thing, you could co-schedule containers. So you'd say, I want to run this container on 5,000 hosts. And then, I also have this other container that wherever that one is, I want one of these, right? But they couldn't really talk to each other. And so pods is much more clever because they get put in the same shared network and storage space, and so they can talk to each other. They sort of have a single IP to the pod, and you can sort of control your own ports and things like that. So it allows for some interesting patterns. So Knative is another project that we incubated in my team, and that ended up also being open sourced, and it's sort of a stateless service. If you have a stateless service, how do you make it easy to just write some code and say, yeah, give me the standard stateless server behavior? Like scale it up to any size, scale it to 0 if no traffic is coming in. So sort of the Lambda or Cloud Functions kind of things. This is an addition on top of Kubernetes. You can install Knative into a Kubernetes cluster, and you sort of get the standard, implemented pattern for doing stateless services, right? So it's one of these building blocks on top of the infrastructure OS, if you will. It's just an example. And Google has a product called Cloud Run, same API. It doesn't actually run on Kubernetes, but it's the pattern, it's the same spec that you provide, and it runs it, on its infrastructure. It could run on Kubernetes at Google, but it just happens to not in this case. Okay, so I guess my message is, if you're building highly reliable, highly scalable systems, Kubernetes is a pretty good starting point, right? It does have a high bar of learning, of sort of understanding. But you're going to need a lot of that capability because you really don't want to build a lot of those things yourself, right? And so when you have, if you can leverage other people have figured out how to build these things at scale, which patterns to use, then you can focus on using your expertise to build the things that actually matter for you, and sort of say, yeah, you know what? I have to configure these things, and then the scaling will be taken care of, right? So you get a lot of the cloud native principles by adopting Kubernetes, but it's as I said, it's a starting point. It's not the whole thing. Yeah. So the CNCF landscape is, if you go Google that, CNCF. So the Cloud Native Computing Foundation is one of the things that we sort of kickstarted as part of Kubernetes to sort of have a place to host these cloud native products, right, or projects. And so there's a whole bunch of things that are in the CNCF, and then they also refer to all the things that are compatible with it. So I guess that's my talk. I think I did okay on time. I hope I didn't speak too fast, but if anybody has any questions, I'm happy to entertain them. There's one right there.
We have a question on the side there, Arvid, please.
Thank you. So, Kubernetes came out in 2016?
2014, I think,
2014.
Right? Well, actually, 1.0 was 2015. Yeah.
Okay.
Yeah.
So, why no support for IPv6 from the start?
Yeah,
I feel that we're losing a lot because of this. Because we see, it feels like this was developed by developers and not by people handling system administration and operations.
Yes, so I agree with the sentiment of the question. I no longer work at Google. I stopped working on Kubernetes in 2017, 18, somewhere around there. But yeah, what I can remember was that there was a lot of hoops that need to be jumped through in order to support IPv6. I think a lot of those were related to Google's internal systems that things needed to be run on. Like obviously Kubernetes could support it, without Google's implementation doing it. But yeah, I would prefer that IPv6 was supported everywhere by everything, but I have no control over Kubernetes in this case. So, yeah, sorry, I don't have a better answer than that. Say it again? Who wasn't?
Can you give him the mic?
Oh. Yeah, I mean, yeah. Right. Yeah, so the building blocks didn't do that.
I was saying that Docker was not good with IPv6 either,
Right.
and it's still not really good.
Right.
So,
Any other questions?
okay.
All right.
Well, please join me in thanking Martin for his presentation. Thank you so much.
Thanks so much.